All right, in the last couple of modules, we've talked about stoichiometric defect reactions, and now we're going to move on to non-stoichiometric defect reactions. And I want to start with pose a question to you. And this will be on the quiz, so listen to the instructions and then pause the video, go over to the quiz, and come back. But the question is, what do you expect to happen to sort of this generic metal oxide that we've been talking about, MO, if the partial pressure of oxygen that this metal oxide exists in is reduced? And so if you're unfamiliar with what that is, think about this metal oxide going into a vacuum where there's less oxygen atoms, or if it's those oxygen atoms or molecules are replaced by inert gas. And so the partial pressure of oxygen is reduced or lowered to some extent. So think about the reaction and think about what you think will happen to it, either in general terms or however you want to talk. And then we'll come back and we'll discuss this before moving on. All right, so let's take a look at that question I posed about a metal oxide in an oxygen atmosphere where the partial pressure is reduced. So again, we're talking kind of like the experiment we talked about earlier with activity, where we have our compound MO, and they're in this chamber, we're reducing the PO2, the partial pressure of oxygen. So there's less and less oxygen in there, and I ask what would happen, right? So this basically discusses what would happen to this oxide if we drive it with oxygen, right? So if we think about the formation reaction, like this, that we've talked about before, right? If we lower the O2 in this case, we're driving the reaction in this direction, right? So by lowering PO2, we're driving it in that reaction. And so we're driving it more towards the metallic form, or we can also think about this as changing the structure. So another way to think about this is we're driving it this way, and so if there's an equilibrium between MO and oxygen, this is going to drive oxygen out of the MO oxide towards the compound. So we might expect that if we reduce the amount of oxygen here, right, the amount of O2 that we have here, O might want to come out of the oxide to contribute to have more equilibrium there and drive it towards this side of the reaction, right? And so this forms what we would call an oxygen deficient ceramic. So it's compensating for the lack of oxygen in the gas phase. And so this, and the reason I bring this up is because this is one type of non-stoichiometric defect reaction, right? Because doing this changes the ratio of M and O, right? If we do this, there's less oxygen in this compound than there would before, and therefore it's non-stoichiometric, right? So that's one type that we can get. All right, so now I want you to take what we just talked about with the MO oxide and the low partial pressure, and I want you to see if you can come up with the defect reaction for that low oxygen partial pressure scenario we just discussed. So see if you can do that, and then we'll come back after you've done that, excuse me, on the quiz, and we will discuss what you got and maybe how that differs from what I've obtained. All right, so let's talk about that defect reaction that you got for low oxygen partial pressure that we just discussed. So if I'm going to write that, we're focusing on the oxygen because that's what we saw is coming out, right? So we're going to write on the reactant side that oxygen is in its proper position and there's no change in charge. And if it's leaving the structure, then we know we're going to have a vacancy, right? So we can go ahead and write that in. We know that we have that. And then we know that the O2 was coming off and contributing to the gas phase. And so we can write that as 1/2 O2, right? For each vacancy, there's going to be a half of O2. And I'll just write that as the gas phase, right? So we know that's the case, all right? But this is incomplete, right? This is not balanced. The oxygen left here and goes here, so that's balanced. The mass is balanced, but the charge is not, right? There's a minus. We know that a vacancy is charged, and a vacancy of this oxygen ion is charged, and the gas phase is not charged, right? And so there has to be something else. There has to be something else along with the vacancy and the gas phase to balance that charge. And so we need something that will oppose the positive 2 charge of the oxygen vacancy. And if we look at some of the species that can do that, what we see is that we'll get, instead of what we have up here, we'll have the oxygen vacancy, and we'll have 2 electrons plus the 1/2 O2. So we're adding the species, and the reason we can think about this is, right, it's, if we're removing oxygen is neutrally charged, but in the species it's in the metal oxide, right, it's charged. So to do that, we have to add those electrons, right? We have to account for those electrons and those leaving behind those 2 electrons. And so that's what we have here, because those electrons belong to the oxygen. And so so what happens is that by doing this, by this kind of reaction, what we see is that if this happens in this low partial pressure environment, we know we get oxygen in the gas phase, but along with that, we're going to leave behind a vacancy, and it's also going to give us 2 electrons, free electrons, and these can easily be promoted to the conduction band and cause electrical conductivity. And so it's you can see in actual metal oxides like this that have this type of reaction, in this scenario where it's oxygen deficient, that these become conductive. And so it can be shown through experiments that it becomes conductive, and that's why we can write the reaction as it is here. So this is kind of what might happen in the low partial pressure of oxygen. So now what I want us to do is examine the other scenario. We have the same metal oxide, same MO, but in this case, we're looking at high oxygen partial pressure. So if we're looking at that experiment, right, the chunk of MO, and then we're adding the O2, it's going up, and so we have more and more O2 in the chamber here. So in this, sorry about the focus there again. In this case, we can imagine kind of the opposite scenario happening, right? Instead of oxygen leaving the oxide to compensate for the lack of O2 in the gas phase, here we're getting more and more O2 in the gas phase, and we can assume that to compensate, to get back to kind of equilibrium, that the O2 would actually want to get incorporated into the metal oxide. So in this case, we can kind of think of this as O2 in the gas phase, right, is going to get incorporated into our structure. And this could happen, and the oxygen could obviously get incorporated a couple of different ways, right? We could think of the oxygen going to an oxygen site, maybe a vacancy of oxygen, or it could go to an interstitial. So I'm going to, and again, this kind of consideration would depend on the relative size of the anion and cation. But for this purpose, I'm going to say that it goes into an interstitial. So we have oxygen goes to an interstitial, and that's going to give us a -2 charge. And again, we're pushing oxygen into it. It's in neutral species, right? So when it forms into an interstitial with this negative charge, it has to compensate. And in this case, if we added electrons, that would bring it more negative. And so what we're going to see is it leaves behind holes, right? So basically an electron hole, and two of those will compensate. So for electron, we denote that with a lowercase e, and electron hole, we denote that with the lowercase h. And so, and again, we have to incorporate that because this is neutrally charged, and when it goes into interstitial, it's ionized, and that means that we leave behind two holes in the valence band. So this is oxygen ionizes and left with two electron holes. And those holes are in the valence band. And again, this would affect the electronic properties of this material, in this material. And so this addition of oxygen, you can either think of it as an oxygen enriched oxide, or we could also think of this as a metal deficient oxide. So this is the kind of scenario that we're looking at in this case. So both of these scenarios, the low and the high partial pressure, high that we're looking at here, the low that we just looked at before, both of these scenarios, we're assuming that electrons or electron holes are generated to balance these reactions. So this is so we have electrons or electron holes balance charge. So this is the case when the cation only has one oxidation state, so something like aluminum, that's 3+, or magnesium is +1, right? That's pretty common for those. However, if we're dealing with cases involving transition metal oxides, then adding or removing oxygen can also be accomplished by changes to the oxidation state. So basically, if we have a transition metal, the oxidation state can change, so we can accomplish that change in charge that we saw up here by that type of change in oxidation state instead of electronic defects. So it really depends on the specific material. So these that we just talked about would be something like aluminum or magnesium that don't have multiple oxidation states. All right, in the next module, we'll talk about what we call intrinsic defects.